One, two, three. Hello, everybody. Hello, hello, hello. You ready to start? Because we are. Okay, welcome, everyone. We're really, really excited to welcome you to Udacity. Who knew Udacity before this invite? Oh, that's almost everybody? Oh, great. Of course you did. So, hello to all of you. Thanks for making it out here. Hello, everybody online. Just want to quickly thank Erin, LeDell for organizing and working with us and bringing you all here. We're super excited and want to welcome you not only to this space at this event, but also to work with us. So hopefully you all saw that we have these sheets on the tables. We're always, for our programs, looking for project reviewers, for mentors, and also for freelancers on a content production team. We're doing really, really exciting things other than our machine learning nanodegree program. We'll talk about in a few minutes. We're also in development of the self-driving car nanodegree program. It's really exciting. Yes. So yeah, we really invite everybody to reach out to us, to apply, to talk to people. We try to, everybody who is working at Udacity can answer your questions and tell you who to contact. Also, I'm Victoria. I'm the project manager on the machine learning nanodegree program team. And we'll now hand over to Arpan, who is introducing himself.
Yeah. Thanks for mentioning who you are, Victoria. She's been an immense resource on the program. I'm a course developer here. I mostly work on the machine learning nanodegree and the Georgia Tech Online Masters program, if you've heard of it. We make the courses for them. So about the program, just a quick brief overview. You can find more online. You basically have to do a series of projects, 5 main projects, 1 optional at the beginning, and we give you some material in order to prepare for those projects. But the material is optional, so if you already have a good background, you can fly through the program. The really neat part is when you submit a project, we have a large community of reviewers giving you very critical feedback on your projects, and you can iterate on them and improve your delivery. And then some of the projects have a capstone component. So in our program, the last project has an open-ended part. So you can take your project in your own direction. You can make a complete app or a service out of it, put it out there, make it part of your profile when you're searching or applying for jobs. It comes in really handy. So yeah, that's about it. Feel free to join the program either as a student or, as these sheets will tell you, we're always in need for excellent reviewers, for mentors, what Victoria mentioned. So you can apply to become one of those people. And if you have any questions, I'm around. Any of the other Udacity folks are also around. Arpan. Yeah. Cool. I think Victoria has something more, something really exciting to share with y'all.
So exciting. One thing I'll say that you missed, we also have careers projects on our nanodegree program path. So basically, you get a review of your resume, your cover letter, your GitHub profile. You can do LinkedIn profile, exactly. And now we also soon have a interviewing course for machine learning. So specifically to when you're applying, interviewing as a machine learning engineer. That will prepare you for that and give you practice, and you can basically send in your responses to questions and get feedback on those so you can better prepare. One thing we did, and hopefully you all saw that, we wanted to give out scholarships to 2 women in machine learning from this audience. And one of the ones that we selected, we got very, very interesting, very impressive applications. That was really wonderful. One of the ladies who we picked, unfortunately, went to SF today, not to Mountain View. It's Lauren Mendoza. Congratulations, Lauren. I hope you're online. She's online? Yes. Congratulations, Lauren. Looking forward to working with you. And Chirinma, right here. are you open to introducing yourself real quick?
Hello, everyone. So first of all, thank you to you guys. I really, really appreciate it. I've been very interested in machine learning for a long time, but you know, having a full-time job and trying to find the time to take the classes and wondering if I should do the nano degree or not, having the scholarship is going to be very, very helpful to me. And hopefully I'll finish in 6 months and we can all celebrate. But yeah, so anything else?
Oh, that's great. Perfect. Thank you so much. We're really excited, and we will follow up with all the scholarship recipients during the program to see and talk about how it impacts their life and their careers. So that will be very, very exciting. And that was all I had. Any questions right now for us before we dive into the amazing topic that are planned for today? Perfect. Then we'll hand over to Erin.
All right. No, I'm Erin, but I'm just gonna do a little intro, and then the other Erin will come up and start her talk. Yeah, just something about the scholarships. So if you're wondering what that was all about, that we sent out an email, I don't know, maybe 2 months ago, 3 months ago, on our email lists asking, or giving a link, and so people applied offline. It wasn't like we just sort of picked people out of a hat as they came in today. So, so maybe you hadn't heard about that. But anyway, it was very generous of Udacity, so thank you for that. And so today's meetup topic is Model Hyperparameter Optimization. So just a one sentence intro of what that means for people that are either new to machine learning or just maybe unfamiliar with that term. It's just a fancy word for how do you find the best model, basically, of all the different knobs and things that you can tune on a machine learning algorithm. It's just a word for how do you do that so that you get the best model. So there's lots of different ways to do that, and we will talk about some of them tonight. And without further ado, this is Erin, who will start us off.
Thank you. Okay, so my name is Erin Craig. Thank you, Udacity. Let's see it. Yeah. This is the start of my slideshow. So I'm talking, like Erin introduced, about hyperparameter tuning. So you've gathered, learning on the fly. Where do I point? This way? Anyway? Yeah, up. Okay, so you have data. You have a model type in mind. You're thinking, okay, I want a decision tree or a support vector machine or a super fancy neural net. And you have some performance metric that you care about. Maybe it's R squared, maybe it's the area under the receiver operating curve, maybe it's the F1 score, whatever it is, you have one in mind. But how do you actually turn all of these things into a model? Models take parameters that you have to specify before you can even begin training. And these parameters are called hyperparameters. So for example, a decision tree has hyperparameters like how deep can the tree be? What is the maximum depth? It can be a super short tree with just one split, or you can let it be super deep with thousands of splits. When you're growing the tree, you have a decision to make about how you evaluate whether or not a split in the decision tree is a good one or not. These are both examples of hyperparameters that you have to specify before you can begin training your tree. And depending on your data and the model type that you've chosen, some hyperparameters are going to make amazing models and others not so much. So if you want to model a super complicated process, like whether or not someone's going to be readmitted into the hospital within 30 days of their release, and you give yourself a decision tree with only one split, then you might have a hard time. Your model might not do that well, right? You're giving yourself one yes or no question to determine, is this person coming back? Alternatively, if you give yourself a lot more splits, you make your tree a lot deeper, you have a better chance of success. So it matters that you get a good set of hyperparameters. And the process of choosing your hyperparameters is called hyperparameter tuning. And that's what we're going over today. There are lots of ways to tune hyperparameters. I definitely can't cover them all. So we're limiting it to just a few. We'll talk about hand tuning, grid search, and then we'll focus on Bayesian optimization. Hand tuning is so much fun. You grab a set of hyperparameters and you train a model and you evaluate it and you look at the score. The fun part is, okay, now you have a high score. You grab another set of hyperparameters, you train another model, now you have a new high score, right? It's like playing a video game, and it's so much fun. It's like Christmas watching this thing train and train and train. And you just do this until you're satisfied. Unfortunately, fun though it is, hand tuning is not reproducible. So the sets of hyperparameters that I might try might be very different from the sets of hyperparameters that you might try. I know that I always try a random forest with lots and lots of trees that are really short. And you might not. You might like a random forest with a few trees that are really, really deep. Totally fine. One is not better than the other. It's just our choices that we make are different. Hand tuning is also called a dark art, which is a really funny name. What I think people mean by that is that it requires a lot of intuition, both about your data, the model that, or the process that you're trying to model, and then the way the model actually grows itself. So hand tuning has its issues, but it's still useful. When you're going through the process of hand tuning, you're learning about your data and you're learning about your model. As we're working towards something more systematic, then we'll talk briefly about grid search. So in grid search, you're trying, in some sense, all possible combinations of hyperparameter values. If you think in code, think nested for loops. Here's a picture of a grid. So suppose I have two hyperparameters, theta 1 and theta 2. So I'm saying for theta 1, we'll try the values 5, 10, 15, and 20. And for theta 2, we'll also try the values 5, 10, 15, and 20. And then for all possible combinations of those two numbers, I'm going to train a model and give it a score and store that somewhere. Once it's done going through training all these models, I look at all the scores and I choose the winner or the winners. Here are the nested for loops as promised. This is a hypothetical random forest training loop. So in this case, which is a little pathological, we would train and test 60,000 models. So if your model takes a day to train or a week to train, this is going to be kind of unreasonable. It would be really nice if instead of trying all possible models, you just tried the ones that looked like they might have a chance of being good, right? You want to try the ones that are good and you want to not try the ones that are bad. And that feels very obvious, but it's actually kind of profound. Bayesian optimization to the rescue. With Bayesian optimization, you're deciding what model to train next based on all the models that you've already trained. Okay, but how do you decide where to look next? That's the magic. Well, you want the score of the next model you train to be big, but you can't be too greedy. No algorithm is going to, you can't just go to an algorithm and say, give me a model with a score of accuracy 1 and then have it like bring you something, right? That's not going to happen. So you want the score to be big relative to the scores that you've seen so far. So let's just do it, okay? We'll choose some target score based on what we've seen. So if all the values I've seen have been between 0 and 0.5, maybe I'll choose like a 0.3. And then I say, I want the score of the next model I train to have a good chance of being better than that one, better than that 0.3. So you take all the hyperparameter sets that you've tried before, all the models that you've already trained, and you split it into two groups. You have one group where it's sets of hyperparameters that correspond to model scores that are worse than the threshold that you've set. The other group is all the sets of hyperparameters that correspond to scores than the threshold that you've set. Greater than, less than, two separate piles. Good so far? Yes. Then you create a density over each group. Here, the blue density is the probability that the model score is going to be greater. That's the density we have over our greater than pile. And the orange is the probability that our model score is going to be less than our threshold. That's the density we formed over our less than pile. Fancy words. This is called a tree-structured Parson estimator, or a tree of Parson estimators. The tree is we split our data into 2 groups, and then over each group, we did a parse and estimator. Yeah? Yes. Okay, from here it's all intuition. You use the 2 densities to choose a set of hyperparameters where the probability that your score is going to be better than your threshold is high, and the probability that your score is going to be worse than your threshold is low. In pictures, that means I want to find a spot where the blue is big and the orange is small. You buy it? Believe me? Okay, we'll do a quick walkthrough. Switch to my computer. Uh-oh, I'm no longer in the meeting. What's the meeting ID? It's easy. Pause. Success. We made it. Okay. So first things first, we choose a function that we want to maximize. In our simple example, I'm not going to choose a crazy model. I'm actually going to just choose f of x equals negative x squared, a frowny face. And we have to choose a domain. I'm going to say let x be between negative 10 and 10. So remember the first step is that we're splitting all the hyperparameters we've tried so far into these 2 piles. So I'm fake giving us hyperparameters that we've tried so far. I'm choosing 20 points, 20 x values, pretending that we've tried these, between negative 10 and 10. And then I'm finding the y values that correspond to them here. And then we choose some threshold that we want to do better than. So I look at all the y values I've seen. And for this example, I took the median, so halfway point between what we've seen so far. And then I split our x values into 2 groups. So the red dots correspond to places where our function is greater than our threshold, and the blue correspond to places where the function is less than our threshold. I use these to create these 2 densities. I just chose a normal distribution. This is not the only way or even the best way, but it is a quick way to make densities. So the blue here, again, this corresponds to the places where our model does better than the threshold, or in this case, negative x squared is bigger. And the orange corresponds to the blue points where we do worse. So we have these 2 probability functions. And remember, we want to find a point that simultaneously maximizes the blue and minimizes the orange. So we do that. And our algorithm suggests that we try x equals 0.22 as the next point. So that's pretty good because we know that negative x squared is maximized at 0, right? And for fun, what we're about to watch is how these probability distributions change as we iterate through the algorithm. So they're starting flat and wide. The algorithm just doesn't know what points are, maximal relative to the others. And as we run through, yay, the blue becomes peaked and narrow around the middle, and the orange stays kind of flat, right? So the blue coming to this peak around 0 is signifying that the maximum is 0-ish. And the orange staying flat, that's because we have points out on the left and out on the right that are both smaller than our threshold. Yeah? Cool. All right, that's the math. Let's actually look at this in action. So in the last couple of weeks, WikiLeaks released a dump of emails from the DNC. And I thought it would be a fun new data set, so I downloaded it. No political statements here, just fun new data set. And I looked at who was sending emails to whom. And I found that there were 3 people that really sent a lot more emails than everyone else. They are Luis Miranda, the communications director, Jordan Kaplan, the finance director, and Scott Comer, the finance chief of staff. What we're about to do is make a model that classifies who or predicts who sent an email based on the text in that email. For proof that these 3 are the most email senders, let's see if we can make this even bigger. This is Luis Miranda, this is Scott Comer, and this is Jordan Kaplan. So when I saw this, I thought, okay, 3 is probably a pretty good number. There's no way I'm going to try to classify, right? There are lots of people in this database. That's too many. But a 3-class classification problem sounds like something I want to try. So what does our data look like? We have a label, which is who sent the email, and then the text, which is actually the text of the email. A lot of these emails are just as boring as the ones you see here. So like, is Martin still happening? And you bet, what works for you? So we remove punctuation and stop words. We have to clean up a little bit. And then we'll do a quick sanity check of our data. So we have 2,000-ish rows. Jordan Kaplan by far sent the most emails with 942. Luis Miranda came in second with about 750 emails, and then Scott Comer with about 400. We do a train test split. I do 70% for training, 15 for test, and then 15 for cross-validation. And then here's the outline of our model. The pipeline is just because I like the scikit-learn function. It's not like a fancy thing. It just means do this thing and then do the next thing. First, we compute the TF-IDF matrix. It's a lot of letters. All that does is it gives us an indicator of how unique a word is in an email. So if I send an email that's just banana, 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 and no one else ever writes about bananas, then banana is going to have a pretty high score for my email. On the other hand, everyone is using the word the, which I've actually removed as a stop word, but as an example, everyone uses the word the. So that would have a pretty low score across emails because it's not a very unique word. We're good-ish? No? Reshare? Coming. Success? Okay, so we have this TF-IDF matrix, which gives us a measure of how unique a word is in an email. And then we're going to train a gradient boosted tree. So first I did hand tuning, which was fun, although I knew I was going to use it as a comparison for Bayesian optimization. So I think I didn't do it as vigorously as I otherwise might have. Apologies. So if we just guessed every time using the class ratios, we would have had an accuracy score of 0.37. I did okay. On the training data, we got an accuracy score of 0.66. On the test, we did 0.56. And then on the cross-validation set, we did 0.62. And then we repeated the process, except using Bayesian optimization this time. We used tree-structured parse and estimators, which we're all experts at now. And I used a Python package called HyperOpt, which is really easy to use and really lovely. So the first thing you have to do with HyperOpt is you have to define the search space. So in our example, we said we were going to try to maximize negative x squared from negative 10 to 10. We're doing the same thing here, except now it's just hyperparameters that we're specifying. So for example, this is the maximum number of features that's corresponding to how many words the TF-IDF matrix is allowed to look at. And I'm letting that range from 20 to 1,000. That means I just really didn't know how many words it was going to need, so I gave it a really broad range to play with. And then we have to define the objective function. This is the thing that we're actually trying to maximize. So the objective function is going to take a set of hyperparameters, our training data and our testing data. It'll train a model on the training data, and it'll compute an accuracy score on the testing data. It returns that accuracy score. In code, this is what it looks like. So we come in, we first train, then we predict, and then we compute accuracy. Go. I was really excited about this part. Then we run HyperOpt. So here we're saying this is what we're trying to maximize, is this function that we just looked at, fit model and compute metrics. Our search space is the space that we saw defined a little while ago. The algorithm is tpe.suggest, so that's the tree of pars and estimators part. Max evals, that's just how many times it's going to run. So I gave it 500. That's a number I just picked. You could pick that number smarter. I just picked 500. I knew I didn't want to try everything in my search space, but I wanted to let it run for a little while. And it returns, after these 500 trials, it returns the model that it found to be the best. So we train that model. On the training data, we now have an accuracy of 0.86 when before we had about 0.67. On the test data, our new accuracy is 0.73 when before it was 0.56. And on the cross-validation set, the holdout set, our accuracy is 0.76 when before it was 0.62. So we did better. Because I'm generally curious about the world. I also wanted to look at feature importances. I know this plot is very hard to read. We will zoom in. In this bar chart, every row is corresponding to a word in the TF-IDF matrix. And when the feature importance graph is shaped like this, it means that it's actually using a lot of the features. When we zoom in to look at the top 10, they're silly words. They're like not very interesting words. The first most important feature is the word 2016. After that, it's Knoxville. Then S4 and time and email. One of them is Trump. I should look at that. That's kind of cool. So these are telling us which words are helping to differentiate between the authors. There's one feature in here that suggests I made a mistake. So this one is S4. I think that's actually in someone's email signature sent from my Samsung Galaxy S4. So I should go back and look at that because that might just be giving it away. And then lastly, I wanted to look at the search space. So what are all the sets of hyperparameters that our algorithm tried? If you look down this diagonal, you'll see how many times the algorithm tried one of those hyperparameters in a given range. So for example, this is the maximum number of features. Most of the time, the algorithm was trying a high maximum number of features. And that makes sense, right? It wanted to use a lot of words when it was trying to discern between these authors. All right, wrapping up. Bayesian optimization is really cool. It's useful for hyperparameter tuning. In particular, we looked at a tree of pars and estimators, and then we went through this example using HyperOpt. Thank you. And are there questions?
Maybe a very good presentation, first of all. Maybe I missed this, but did you also compare grid search with the Bayesian method?
I didn't. I got lazy. I really I have personal, I don't love grid search. So yes, thank you for asking. Good question and great point. Others? Yes.
For XGBoost as well as other, especially in scikit-learn, there's a lot of parameters. Like, how do you choose which parameters that you want to tune even sometimes?
Yeah, so that I think is in general a hard question and depends a little bit on your data and the models that you've chosen. I tend to be of the philosophy, so take it or leave it, that I like to throw everything in and just see what happens. You may notice that there are parameters that it sort of doesn't matter what you do with them, and maybe just hold those fixed, but otherwise I like to throw the kitchen sink in and just see how it works. It's the Olympic torch.
So you mentioned about objective function. So sometimes we might have to have more than one objective functions. So is there any reason or rationale behind what objective functions to choose, and some research on that lines?
Right. So do you mean, for example, I chose accuracy and that, yeah. I've been thinking about this lately, actually. I'm glad you brought that up. So for me, I'm a little bit unsatisfied with having to choose just one. And right now with the way Bayesian optimization is set up, you have to have one function that you want to optimize. It doesn't matter what's in there, but it's just one thing. So I'm really curious about, and have not done any work yet, but I'm really curious about how we can combine these different performance metrics so that in Bayesian optimization, we're getting something that perhaps is a little more meaningful. And as always, the objective function that you choose is going to be a function of your data and your goals, what you're trying to do with that data. So if you have imbalanced classes, for example, you might choose a different metric than if not. Did I answer your question? Yes, thank you.
What kind of models can you tune with this method and would work well?
Sure. So Bayesian optimization is a general technique. You can really throw anything in. Like, it doesn't need to know what's inside the box. By box, I mean function that you're trying to optimize. So for me, I mean, I think it's a little bit of a free-for-all. In fact, so going back to this, I like to throw the kitchen sink in. I've used Bayesian optimization to simultaneously optimize like what the shape of my data should be, as well as what features I should use. I know I really went for it on this, what features I should use and what the hyperparameters of the model were, because I really wanted the optimal combination of those things. So my philosophy is throw in whatever you want. In reality, it does take a while. So you don't necessarily have to evaluate as many models as you do with grid search, but you might have to evaluate a lot. So if you're training a neural net that takes a week to train, that might be difficult. That might be a bad choice for this. But otherwise, I think it's pretty much a free-for-all in terms of what will work and what you want to do with models.
But does it work well for neural nets, which are non-convex?
I've never done it for neural nets. Other people have, and they've had great success. Yeah. Cool. Thank you.
So we have our next speaker up, Alexandra. Okay. I'll just stand here and watch you tie your shoe. You're quick.
Yeah. Oh, so which way does it just click it? The right one. Okay. Good thing I can tell my right from my left. Okay. Hi, I'm Alexandra Johnson. I'm a software engineer at SIGOPT, and I'm here to talk about Hyperparameter Optimization 101. Erin just gave a great introduction to hyperparameter optimization and went into a deep dive of a lot of the different methods, including grid search and Bayesian optimization. SIGOPT is backed by a variant of Bayesian optimization, so thank you so much for the wonderful explanation. What I'm going to do is I'm going to give my own definition of hyperparameters and hyperparameter optimization, and then do a deeper dive into the mechanics of how specifically you will optimize your models, as well as some of what we're doing at SIGOPT to rigorously compare different hyperparameter optimization strategies. So hyperparameters, as Erin said, they're like the magic numbers of your model, right? So like with the number of trees in your random forest or the depth of each tree, you set your hyperparameters, then you add in your training data and you train your model. Hyperparameter tuning, hyperparameter optimization, Erin LeDell said this, all terms for the same thing. It's finding assignments for your hyperparameters that make your model perform the best. This is going to be the biggest point of the thing, is that hyperparameters affect model performance. Cannot say this enough. Hyperparameters affect model performance whether or not it's accuracy, it's error. They can also affect things like the amount of time it takes to train your model. They can affect the amount of time it takes for your model to respond with a prediction. And so there's many varied ways, kind of both expected and unexpected, that hyperparameters can affect your models. And so that's why they're so important to machine learning, because they have so many varied outcomes. So when it comes to optimization, first step, to pick an objective metric. And so like I was saying, this is where you can do things like accuracy, like with the DNC emails. You can also look at error. But again, if you're trying to maximize, then you want to take the negative of the error. This is where you can combine multiple objective metrics. If you wanted to combine several different objective criteria, you can do a linear combination. You can do something more complicated. You can try to optimize two different things in parallel. You can also build in like a linear combination, a penalty score for models that take too long to train. A great example is that if you're looking at n-grams, longer n-grams will take more time to compute and more time to calculate with. And so you might say, if my model takes over 2 hours to tune, I want to say that it performed as poorly as it can. I want to give it a score of 0. And so that I will not consider models that take more than 2 hours to train. This is a really big point. Cross-validate your models during optimization. Touched on it during the last talk. You want to build this on top of your objective metric. Once you've picked an objective metric like accuracy or root mean squared error, you're building a function, and that function goes from assignments of hyperparameters to a real number output. You want to cross-validate inside that function. For every set of assignments of hyperparameters, instead of calculating the accuracy once, or instead of calculating the error once, you want to form K, and where K is, we think 5 is generally appropriate. You want to calculate 5 different train test splits of your data and calculate your objective metric 5 different times and take the average of that. This process of kind of iteratively train test splitting your data set and calculating the average and reporting the average accuracy is cross-validation. Cross-validation is important to avoid a problem called overfitting. Overfitting is an issue where the model is too attuned to idiosyncrasies in your training set. This is something that people run into a lot when they use smaller data sets. And this is something that happens in practice when people perform hyperparameter tuning without proper cross-validation. Hyperparameter tuning is very efficient at optimizing a model. A model is very efficient at learning a data set. With no cross-validation, your model will become highly tuned to things that are only happen in your data set, and your model becomes not well representative of what happens out in the wild. So long story short, to avoid the problem of overfitting, cross-validate your models, and they will perform better when you expose them to new unseen data that comes outside of your train and test set. The second step in this process, once you have set up kind of a function that goes from assignments of hyperparameters to a cross-validated objective metric, you run an experiment. Since SIGOPT is backed by Bayesian optimization, this is a little bit tilted towards the Bayesian optimization side, but n times you want to get a set of assignments of hyperparameters, evaluate your model using the cross-validated objective metric, and record an observation. You do this for grid search, you do this for random search, and you do this for Bayesian optimization. What you get is you end up with n points in your parameter space and n values of your objective metric. You can write them all down in a list. You can store them in an Excel spreadsheet. But the goal is that you have these kind of endpoints in your space. often n is set beforehand. And then in the last step, you want your model to perform as well as possible. And so you find the best value from the last step. You get the corresponding hyperparameter assignments. And then you'll train your model on all available data, because you're kind of out of the step of needing to cross-validate your model to find the right hyperparameters. At the step, you have already found the optimal hyperparameter assignments. And so you're training on all available data. And then your model is ready to deploy into production. So now that you've, trained and optimized your model and it's performing as well as it can, you might ask yourself, so you use that method to train and optimize one model, but how do you compare between different optimization strategies? You might use the last step just with grid search or only with Bayesian optimization, but how do grid search and Bayesian optimization perform against each other? Some nice GIFs of grid search, random search, and Bayesian optimization as were introduced in the last talk. Grid search, what I think is interesting is it's a deterministic process. It can be used to optimize stochastic models, but random search and Bayesian optimization are clearly stochastic. And by stochastic, what I mean is the process by which they choose points in the hyperparameter space to evaluate is stochastic. I mean, random search is the definition of randomness. You're choosing random points in the space. So instead of just looking at one time that we tuned our model, we look at 20, 30, 50 times of tuning a model. What we did here is we ran 50 experiments. 50 times in a row, we started from scratch, and we tuned a classifier on the iris dataset, and then we looked at the best value achieved by that model. What you'll notice is that you're seeing different maximum accuracies, and again, that is because we're using a stochastic process to train a stochastic model. The dashed line in the middle represents the mean, and our view of how well this hyperparameter optimization strategy is performing begins to take shape. Here we're comparing several different hyperparameter optimization strategies. You can see there's pink, cerulean, and cornflower. And that's my nod to Devil Wears Prada. Please go look up the rant of cerulean belts if you've never seen it. We can see that the pink looks like it's clearly outperforming the cornflower and the cerulean. But we kind of are not getting a great view of what's happening between the two blue models over on the left-hand side of the screen. We have a rough ordering of how of the mean dashed lines, but we want to be able to actually make assertions that are backed with statistical confidence about which strategies are outperforming the others. And so to compare with confidence at SIGOPS, we employ a tool called the Mann-Whitney U-test. And the Mann-Whitney U-test is like the t-test. It will tell you whether or not two distributions are drawn with confidence from different underlying populations. But unlike the t-test, it does not require the assumption that your distribution, your histograms, are normally distributed. And so it can be applied more broadly. So sometimes this will give you the answer that yes, your two histograms come from different underlying populations. Each histogram represents a different optimization strategy. When you get a yes answer, what that means is you can say, okay, now I compare the means, and I can say that statistically, with a p-value, one hyperparameter optimization strategy is better than the other for my problem. You can also get a tie. In the event of a tie, what you want to ask yourself, this really important question. How long is your experiment? How many points in your hyperparameter space are you required to evaluate to optimize one model? This is a reason people might not be fans of grid search, is that grid search grows exponentially in the number of parameters that you are trying to optimize. What we did is this basically shows dividing each parameter into 10 segments. Most people would not be able to use this method. Most people, when they have 6 parameters, can only afford to evaluate the model on each edge of the hypercube of the parameter space. Because of the curse of dimensionality, grid search becomes intractable in spaces of higher dimensionality. Random search, I have not seen yet clear guidelines on how many times people run random search, the number of times they evaluate their model when using random search. And for Bayesian optimization, we've seen in practice that it's good to run between 10 and 20 times the number of parameters evaluations to successfully evaluate your model. And so Bayesian optimization has the advantage of growing linearly with the number of parameters rather than exponentially. So to recap, hyperparameters affect model performance. Hyperparameters affect, classical, how well can my model predict a number? How well can my model predict a label? But they can, okay, I'm loud enough to shout if we, but they can also affect the amount of time it takes to train your model, which is a very important practical consideration that we have in machine learning. You should always cross-validate your models to avoid overfitting. So cross-validate your models during the optimization step. And then when it comes down to comparing optimization methods, you want to look at which method found the best found value, but you also want to ask yourself, how long is my experiment? So a little bit about SIGOPT. We, as I said, provide an ensemble of Bayesian optimization techniques. We have used these evaluation methods on ourselves and found that we compare very favorably to open source methods like HyperOpt and grid search and random search. We have some really great blog posts that have been put out by our research engineers on tuning, using TensorFlow, tuning convolutional neural nets, as you were asking about using hyperparameter tuning on neural nets. We found that the baseline TensorFlow on the MNIST digits data set was about, using convolutional neural nets, was about 19% accuracy when TensorFlow was untuned. Tuning TensorFlow with SIGOPT boosted the accuracy by about 315%. And there's a great blog post behind that and behind with an example of how to actually run the TensorFlow code if you've never run TensorFlow code before. We really think that it's important. Machine learning examples that are very easy to use. And we've also have another blog post on using XGBoost with unsupervised features. And we achieved a 49.2% lift in accuracy over the untuned method using raw features. And so that's another great example of how you can use hyperparameter tuning with feature selection, as has been brought up. So SIGOPT also provides an easy-to-use REST API. I work on the platform, so the API, the web interface, and our R, Java, and Python clients. So we have a REST API, which means you can use it in any language as long as you can write a wrapper for a REST API. There's no setup on your end. There's only 3 simple API calls to get up and running, optimizing an experiment. We offer visualization and parallel management via the API, and we've got a great 3D visualization of tuning a classifier on the Iris dataset. And we have a free trial, an academic discount, and we're hiring for both internships and full-time. If you're interested in learning more about what I just talked about or about Bayesian optimization in general, we have some really great resources on sigopt.com/research, including a paper that was presented at ICML this year, which is the basis for a lot of the later half of my talk about evaluating hyperparameter optimization strategies. And I would highly recommend that you check that out. All right, are there any questions? Or feel free to visit our website and blog.sigopt.com. Any questions? Yeah.
Hi. I was curious if you could talk a little bit more about the ensemble of Bayesian optimization methods. Does that mean you're running a couple different ones and then sort of averaging the results in some way, or like maybe you could talk a little bit more about that?
Actually, if you want to talk offline, I can connect you with the research engineers who work on the optimization core. I do not know the specifics about that, but I would be happy to give you the email address of people who would love to talk to you about it. Yeah.
So I've been using SIGOP for a few months, and I have been get this experience of using SIGOP just training on a smaller data set because the iteration time is much shorter. So I have a very big data that I can train from, but the training time for a larger sample will take a much longer time than a smaller set. So I use SIGOP and define the evaluation metric to be accuracy on a smaller data set and use cross-validation. And you were just mentioning you can build your models and ask SIGOP to find your best performer with a sample of data, and then put this train your model on and train on your entire data set with the best performer. Can you talk about how what is the split? Like how would you see the strategy of putting how much data into your training and then test and validation, and how is the best number to say I'm confident to put this into production?
So you're talking about, I sense a couple questions from there. So one of your questions was, what is the optimal train test split during cross-validation?
Yeah, but that's we have a convention of putting it into 70 and 30. But
Yes.
different people have different preference. But I have this this battle for training a bigger data set, but takes longer time, and then training a smaller data set, but use cross-validation, which could also take longer time because the more your cross-validation parameter is, it's gonna request more evaluation. Right?
Okay, so Olivia is mentioning is kind of the trade-off between how much data do you train your model with during the optimization step, because as you're right, there are a lot of iterations that go into cross-validation. There are a lot of iterations that go into hyperparameter optimization. And so the part of your question where you asked about the train test split, we do use a 70-30 train test split in most of our examples with 5-fold cross-validation. So 5 times we're dividing our data set into a 70%, 30% split. And then we're training our model on 70% of the data and testing on 30% of the data. And we're doing that 5 times in a row. That's usually because we have smaller data sets. You know, I don't know what the best answer is to your question about how many times you should do this with larger data sets. I would always recommend always cross-validating at least a little bit on all of your data. And we do think that 5 folds with 70-30 split is appropriate. You know, the more data you can put into your model, the better it can perform because it will see more examples. And so this is an area that I think would be really interesting to look into. And I'd love if anyone had any examples they had run on it to see if there was like a better split that you could form for holding out in the optimization step and then training with all of your data, you know, maybe doing like a 10%, 40% split instead, but I don't have a good answer for you at this time.
Yeah, I think my point is how at what point you're confident to say, because the accuracy of SIGOP depends on how much data you give to it, right? But at what point you are confident to say this is the best performer based on the minimum number of sample data I can give to it, and I can put this into production and run this on my entire data set. Is that clear?
So the kind of minimum accuracy or the minimum accuracy, is that what you're?
The minimum time you need to take on training the data and say this is the best performer with limited resources.
So we would say for Bayesian optimization in general, what you want to do is you want to run between 10 to 20 times the number of parameters you have in your hyperparameter space. You want to run, you want to evaluate 10 to 20 times the number of parameters points in your hyperparameter space. I want to give I would love to give someone else a chance to ask a question if they have one. I'm happy to chat with you offline about the question. Is there? All right. Thank you so much, and get ready for Erin LeDell.
Thanks, Alexandra.
Can do one. Okay. Yeah. There's some. Well, I'll just let me ask you something. There's a link that I'll be going to, but I wanted to like scroll down and go through some code. I could either do the Blue Jeans app. You don't. I don't want to do that. Okay. Okay. Sounds good. All right. All right. Okay. So this last talk is I kind of just like snuck myself in there because I have like, I guess, the authority to do such things as the meetup organizer. I thought it might just be fun to throw in a talk that's related, but it's more like a not necessarily a counterpoint to Bayesian optimization and hyperparameter optimization, but more like a different approach to achieve the same goal. So what I'm going to attempt to do is try to convince you that if your goal is to get a model that's the best model, then you should do all the things that these other women have told you about. But in addition to that, you could also ensemble models together once you've found like the best model in each class, and then get like a better model than what you would have gotten if you just looked at random forests or just looked at GBMs or just looked at one type of model. So this is the type of machine learning that I am very interested in. It's sometimes called ensemble learning, and the specific type of ensemble learning that I'm going to talk about is called stacking or super learning. So I'll first kind of like explain what this is, and then I'll attempt to like convince you that it's a good idea. Okay, so, and this is, so part of this is actually very related to random grid search and grid search. So, okay, so this is just my generic like introduction slide, but just so you know who I am, so I'm the founder of this meetup, but I think I've only given a talk once before. So that was a couple of years ago. So this has been around for since 2013. I work at a company called H2O, which is not too far away from here. So it's right down the street. And H2O is a company that produces a platform for doing machine learning that is open source, and it's called H2O, unsurprisingly. And it's meant for big data. So the idea is that it's software that can run either on your laptop or on a big cluster, and basically you write the same type of code. We have like a Python or R API or a Java API or a Scala API or a GUI. And if you don't like to write code, and then basically just run it. I think somebody on our Slack the other day said that we should say run, what did he say? I think run once, scale big. What was it? Oh no, I can't remember. Now it sounds dumb, but it was like, yeah, okay, never mind. I messed it up. It was funny though. It was like run once, scale big, or so, I don't know. Never mind. Okay, so here's like the agenda. So I'm just going to explain just a little overview of ensemble learning, and then I'm going to talk about what stacking is, and then I'm going to talk about sort of the computational differences between doing a grid search and doing an ensemble, because they're fairly similar. And then I'm going to just mention, so we did talk about in the other talks what what regular sort of, it's also called Cartesian grid search, where you do all the different combinations. Actually, Alexandra mentioned random grid search as well. So the idea with that is you just sample from a big space and just sort of at random, and then at some point, you know, cut yourself off and say, I've done enough model training and I'm just going to choose the best model from this group. And then I'm not really going to do a code demo because it's like too hard with the streaming, but I'll point you to some code and maybe kind of like walk you through it. It's on GitHub, so you can just visit it on the browser. Okay, so this is just in general, what is ensemble learning? So maybe a lot of you already know this, but the idea is just to use multiple algorithms and combine them together in a way such that you end up with sort of like this super algorithm that takes input from all of the ones in the model or in the ensemble, and you get a better performing model than if you were to use any of them individually. So that's the general idea. And there's a couple different types of ensemble learning, so that's a pretty generic term. The three most maybe common types that people talk about are bagging, boosting, and then stacking. So most people actually just talk about the first two and leave out stacking for some reason. So bagging, an example of, well, maybe I should say a little bit about what distinguishes each of these types. So bagging, the idea is, so an example of a bagging algorithm would be random forest. And the idea with that is you average a bunch of models together to reduce the variance of the individual models, which might not be so good. And then you get a better estimate. So that's kind of like a wisdom of the crowds type thing. So like overall, like people aren't that smart, but if you combine them together, they're like kind of smart. So one thing that's good about bagging is that it's robust against outliers. So if there's one person that's extremely, you know, maybe I shouldn't use people as examples. One model that's extremely dull, then it's not going to mess up your model because it's just one person or model. And, you know, the same with like if you have somebody that's really brilliant, it's not going to make your whole model be brilliant. It's just, you know, not going to hurt things. So random forest is an example of a bagged, it's a bag of trees basically, with some other things thrown in. Then there's boosting. So GBM, gradient boosting machine, is sort of a modern example of boosting. So the idea with boosting is it's more of like an iterative process. So with bagging, you could train everything in parallel and they don't need to like really talk to each other. So it's easy to scale. Boosting is a little bit more tricky, although H2O and XGBoost have a distributed boosting implementation, which is a little bit tricky to do because like I said, it's an iterative algorithm. So the idea is that you train sort of like one tree and then you figure out where that tree did a bad job, and then you either like, it's not really correct to say upweight the examples that did poorly, but essentially that's what you're doing. So if you're basically telling the algorithm, okay, pay more attention the next time to these ones over here because they did a bad job. So then you do it again, and then the next time you're sort of focusing in on the ones that were more difficult, and then you find the other ones that were bad the next time, and you sort of keep doing that until you get a good model. One of the issues with boosting, although in practice it's not really that much of an issue, but in theory it's not necessarily robust against outliers. So if you have some really bad data in there, it's going to keep trying to fix itself and sort of adjust itself to this bad data, and that might cause overfitting. But in general, there's a lot of different tuning parameters that you can use to sort of compensate for that. One other thing that's really nice about boosting is that you can use any loss function. So depending on whatever metric you're trying to optimize. So a lot of businesses use this because they can take whatever their cost function or whatever it is that they're trying to optimize at their business and like convert it into a function that they can optimize in a GBM. So that's one reason why it's popular. And then the third that we're going to talk about a little bit more is stacking. So the difference with stacking is sort of twofold. One, rather than training models that are the same, so with the two examples I gave, you would train a bunch of decision trees and do something with them. So with stacking, the idea is you train a bunch of different types of models. So maybe like a random forest and an SVM and a deep neural net and a whole bunch of other things. So you want to have a diverse group of learners, and then the other thing is you actually, instead of averaging or doing something sort of simple, you use machine learning to learn what the best combination of the learners is, or the models is. So there's two levels of machine learning happening. So there's training all the models or cross-validating all the models, and then you do another. I'll explain sort of more in detail on the next thing, but basically it's machine learning on top of machine learning. So I'm going to just attempt to explain the algorithm, and it's actually not very complicated. So if you want to try to follow along, it's if you understand basically what cross-validation is, actually that's all you need to know really, is what cross-validation is, and you should be able to grasp what's going on here. So here's like your typical setup in a machine learning problem. So we have training data, which has n rows, so n training observations, and let's say there's m columns, and we call that x. And the columns are all the different like features in your data. And then you have your response called y, and maybe that's like a binary response, zeros and ones, or maybe it's some number like a regression problem. It doesn't matter. So you have your data, and then you kind of have to like set up your algorithm. So one thing you have to do is you have to choose what you're going to put in the ensemble. So you basically specify all these base learners. So when I say specify, I mean basically define which algorithm you're going to use, and then which set of parameters you're going to use in that algorithm. So basically you say, I want to train a random forest with 100 trees and max depth of 4, and everything else defaults or something. And then I want to train a deep neural net with this particular type of architecture and this and this and this. So fully specified models. And then the second piece of machine learning that I mentioned that is called the meta learning step. So when you're machine learning on the machine learning. And then you just use another algorithm for that. It could be any algorithm. So maybe you would use just like a GLM. So GLM is popular, even though that's not like that great of an algorithm overall. It works well for meta learning. But you could use anything. Some work better than others. So then once you've specified, basically laid out a plan for what you're going to do, then what you do is you do k-fold cross-validation on all of those base learners, and you'll see why you do that in a second. So when you do k-fold cross-validation, it could be 4-fold, 5-fold, whatever you want it to be. One of the things you get in return is a list of, you get a predicted value for every single observation in your training data. So, on the first iteration, let's say of a 5-fold cross-validation loop, you train on, 80% of the data, and then you test on 20%. And so you get predictions for each of those 20% of the data points. And then you do that 5 times, and then you actually can sort of reassemble them together. So you get a big column that's n rows, and then just predicted values for each one of those. And then, so that's sort of like what you get out of cross-validation. And then typically what people use it for is then from those predicted values, they also know the labels. So then they calculate some cross-validated metric to evaluate how well the model performed. But in this case, we're just going to grab those predicted values and stack them together, like column bind them, if that makes any sense. So think about them like standing up together next to each other. So there'll be like L learners in your ensemble. So let's say L is 10. So we have 10 models in our ensemble. So we get 10 columns in this new matrix that we'll just call Z. And there, there's n rows. And then we just do another machine learning problem. So we just take our meta learner and train this, make that be our training data, and then we're done. So if I'll summarize kind of like what we have at the end of this process, it's basically we have a set of models that can make predictions, and then we have another model that takes those predictions as input and then spits out the final answer. So it's kind of like a two-step thing. So you give your, say you're trying to make a prediction on the test set, you first ask each one of your algorithms, what's your prediction? And then you take those values and you give it to the other model, the meta learner, and then as input, and then it spits out the final answer, which is your ensemble prediction. And so that's basically what's happening there. So, yeah, let me talk about now how this relates to the rest of these talks. So basically, if you think about what we've done to train the superlearner, is basically do a bunch of k-fold cross-validation. So we did cross-validation on each one of our candidate learners or base learners. And if you think about it, that's exactly what you would do if you were doing, if you were just trying to choose between them, which one is the best. You would do cross-validation, 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 and then you would select some metric, and whichever one had the best cross-validated, let's say MSE or AUC or whatever it is, then you say, okay, that's the best one, and that's the one I want to choose to be my model. And so you're doing the same thing with like Bayesian optimization or any of these other methods. You're just, and sort of Alexandra had this nice like circular thing where you go through and you give it a set of model parameters, then you train the model, then evaluate the model, and then like store that somewhere. And then once you're done with all that, you figure out which one did the best. So what I'm proposing here is that rather than throwing all those models away and just selecting one, you can actually just combine them together and get a better model at the end. So basically, and then the other argument behind it is that this is computationally very similar. So you're already doing all this work to get to do the cross-validation, and that's the thing that costs the most time. So rather than, I guess, maybe it's dramatic to say throwing it away or whatever, but rather than leaving all that computation on the table, you can just make use of it. And maybe some of those models are not good, and that's fine, because your meta learner will figure out which ones are good and which ones are not, and it will just ignore the ones that it doesn't need. And so you don't have to necessarily choose among all the different models. You can just use them in your superlearner. So with one extra step, which is doing the meta learning, which is actually not very expensive compared to all of the other steps. And so I'm just going to point you to a way to do this, which is there's a couple different packages. Most of them are R packages, but we're working on a Python package theoretically. Ray and I are doing that. Yeah, we're working on that. So it will be in Python soon. But basically, this is just a way to do this. So H2O is a package that has a whole bunch of algorithms. So as somebody who's interested in ensembles, I thought it was a good idea to take a package that already had a bunch of algorithms implemented. I wouldn't have to do any of that myself. I could just write the stacking code and use H2O as like a base to create this H2O ensemble package, which is a package that I've written. And so this is just like a few code examples. This might be sufficient. I don't know that we need to go over all the code that I have on GitHub, but basically this is just some R code that shows you how to do like just a regular grid search in H2O. So in this example, we're going to do deep learning. So that's kind of a generic term, but in the H2O world, it means a fully connected multi-layer perceptron. If anyone is familiar with that type of architecture. So it's just a type of neural net. And there's a couple things that we're going to look over or like grid over. So one is the architecture of the network itself. So that's what you see over here. So this probably doesn't make sense to you until I explain it, but basically there's three different architectures that we're looking at here. One is a neural network that has 2 hidden layers, each with 200 neurons. The second one is architecture with 3 hidden layers, 100, 300, and 100. And then the last one is 2 hidden layers again, but 500 and 500. So those are just, so the architecture of a neural network can be considered a model parameter that you can tune, because it's just another thing that you can modify and see how it affects the performance. And then the other thing that I'm going to look over is the L1 regularization term. So that's just another thing in a deep neural net that you can mess around with. So this is just an example of how we would do just a normal Cartesian grid search. So it would do, I guess, you have 3 times 2, so, you know, however many, whatever that is. I have a math degree, but it's too hard. So yeah, so all the combinations of those 3 things. So if somebody wants to shout out what the number is, you can feel free to do that. 6? No. Okay. So, all right. So then the other way to do this is we can say, let's take that same grid, or you could define a new one. Probably you want to define like a bigger grid. And we're going to, instead of doing all the different combinations, we can just tell H2O to randomly sample from that space. And so actually Ray, who's sitting right there, wrote this. Thank you, Ray. So I was pretty excited when we got this in H2O, because what that means for me is that I have a way to generate a diverse set of models very quickly and very easily with like one line of code. So rather than me, so when I first wrote the H2O ensemble package, I had to sit there and think about all the different models that I wanted to put in, and I would sit there and like, you know, write out tons of parameters, and like takes forever, and you can't even like think of all these parameters. So this is just a really easy way to say, give me a really diverse bunch of deep neural nets, and then you can tell it how long to go. So there's 2 ways that you can control this. So this is an example where I say max runtime seconds is 600. So what that means is do this for 10 minutes and then just give me what you have after 10 minutes. So train as many models as you possibly can in 10 minutes and then stop. You can also just say max, I think it's max underscore models is equal to, 40, which would mean train 40 models and then stop. So there's ways to control like how long you want this to go on. Okay, yeah. So you can tell it stop when things are. Okay, so I don't use that one, maybe I should. So there's another version where you can, where rather than telling it to stop based on some arbitrary number of seconds or number of models, you can tell it to stop based on some metric that you're interested in. So if I want the AUC to stop, so basically, I just learned about this 1 second ago, but I'll try to explain it. I guess I actually think I knew that that was in there. I forgot about it. So basically what it does is you say, I care about AUC, so that's the metric that I'm going to evaluate on. And then I care that, that if you sort of have this list of models going along and you sort of sort them by their performance of AUC, maybe the top one is 0.9 and the next one below is 0.8999. And then you keep getting models and sort of that last little bit of difference between the top couple of models is so small, you can specify when to stop. So if you're starting to get models that are all very similar and very, like all the top models are the same, then you can stop based on that. And that's probably that's a more intelligent way to do this. This is kind of like, I don't feel like waiting around for a while, so I'm just going to say that I want this to happen. So, which is also a valid way to do things, but more from like a your own time optimization rather than machine learning. Okay, so basically you can run this grid thing, and so you can run it on deep learning, you can run it on GBM, you can run it on all the different algorithms, and it will spit out basically a list of models. And then what you can do is, so I'm not going to go to this actual link, I'm just going to show you the example code. But if you go to that link, that will take you right to a code example of doing everything that I'm talking about. So let's say each one of these is like the result of one of those grid searches or those random grid searches. So you have a bunch of different GLMs, a bunch of different deep neural nets, a bunch of different random forests and GBMs, and then you just stick them in a list. And so now you have a big list of models of all types. And then you can use this stack function, h2o.stack, and you just give it a list of models and you tell it what meta learner you want to use. And there's different, I didn't give an example of how this actually works. So assume that this was specified somewhere else where you're telling it that you want like a GLM with non-negative weights or something like that. And then you need to know what the response is to do the meta learning step. And then it just figures out the optimal combination of those models, and then it saves that. Yeah, you have a question?
So when you have this, you define the list.
Mm-hmm.
When you define the I can speak loudly. That's
all right.
You can use that.
So when you define that list there of GBM, random forest, and other models, so have you already performed the parameter optimizations and selected the best model there?
In this case, no, but well, I guess the way that this code is written, it could be either. But the idea, so there's kind of two approaches that you could take. So one of them is just throw everything that you got from the grid search in there, and then you get a diverse group of GBMs, a diverse group of random forests, etc. The other way that you can do it is you can use random grid search, or you can use one of these other techniques to come up with the best GLM, the best deep neural net or whatever, and then you would have like 4 models. So that's actually a lot of times how I do it. Like, it depends on what my goal is. So if you want a more simple model, you would do it where you just take the best from each and then ensemble them together. And if you basically, if you want to keep like squeezing out more performance, you just shove in more models, and then you just, there's sort of like there's like diminishing returns at some point. So you might get just a tiny little bit more performance if you dump in like 100 more models. But if you're in some industry where you actually like that's so important to you, or it's worth money somehow to your company, then it might be worth it. So one thing about, I think probably one of the main reasons why people don't use this stuff for more often is because there's sort of the sense that it's this complex thing, and there's all these models, and every time you want to make a prediction, you have to make, 10 predictions or 100 predictions, and that's how it works. So if you want like, sub-millisecond response times on your prediction, predictions, you probably just want to use a GLM and just be done with it, So, but if so it's sort of a trade-off. If you want it does take a little bit longer to make these predictions. And it certainly takes a lot longer to train the model than it does to train one model. But if you consider like all the training that you do just to get to that one model, then it's about the same. So it depends on what your setup is. So yeah, so there's all different ways that you can sort of come up with these groups. Did I see a hand go up there? Okay, yeah. I'll just repeat her question. So you said this will have a runtime cost to actually doing the prediction. Yeah. So if you have it set up so that all of these predictions are generated in parallel, and then you do that, and they're probably not going to all take the same time. So if one of these is like a very, very big tree or random forest, then it might take longer than your GLM. So in theory, you could run them all in parallel, and then there would be one more step, which is doing the meta learner prediction. So yeah, it does take longer. So that's something to keep in mind. Okay. So this stack interface is sort of this like the second iteration of the H2O ensemble interface. So the original one, which is called H2O.ensemble, would just sort of require you to specify everything a priori, and then you say, I want this and this and this and this and this in my learner in your ensemble, and then it has to go and train them all, and then it goes and ensembles them, and then yeah, so that's just two different ways to do the same thing. But more often than not, lately I'm using the stack interface, and I'm just training a random grid and putting it in there, or picking the best model from each of the random grids. So here's just some more stuff if you want to learn more about ensembles. So these are all related to H2O. There's actually not that many packages that do this type of thing. There's two other ones that I've written, but one of them I've written, one of them that I've contributed to. The original package for this is called SuperLearner. It's an R package, and that was written by somebody who worked with my advisor before me at Berkeley, and then I took over after that a little bit and added some things. And then there's another one called Subsemble, which is kind of a weird name. Subsemble. It's hard to say. So that's a different version of this where you train on subsets of the data and ensemble these together. And then there's at least one other one that I know of that's called Carrot Ensemble, which is actually, I have checked a couple times, and it doesn't actually implement the superlearner algorithm. It does it's sort of like a shortcut version, which actually Brandon back there has used it, and so he's maybe knows a little bit more than I do. But so I've used it a couple times just to test it out. But basically, instead of doing the whole cross-validation loop, it just does like a bootstrap sample or something like that, or a train test. So it's kind of shortcutting having to do this whole thing, but the ensemble doesn't work as well, but it's faster. And then this will be available in Python hopefully soon in H2O. And those there's Weka, that's another one that probably not a lot of people use anymore, but I think that was the first implementation of this. But that's all I'm aware of. So there's not that many, because I think the thing is, you have to have a whole ecosystem of machine learning algorithms that kind of speak the same language in order to build one of these. So it's not, that's probably why there's not too many. And this is if you're an R Python user, if you want to learn how to use H2O's R Python interface, you can go to that link. And I'll put these slides up on our meetup page too. That just links to some training materials. And this just says what it is. So the intro, there's like two modules, intro to H2O algorithms, and then like a grid search, more in-depth tutorial. And here's just a whole bunch of links. So we're open source, so we put all of our code online, but we also put a lot of trainings and meetups, like presentations and all this stuff. So if you want to learn more about H2O, that's where you can go. And then that's where you can contact me later. But I'll put these slides up on the website later. Okay, so thank you.
Erin, I have an online question.
Yeah.
So guest 20 is asking, what are some of the areas or domains where this algo would be a good candidate, especially ML super learning compared to other forms of ensemble learning? Or
I guess it's applicable anytime you care the most about the performance of your algorithm rather than like runtime or complexity. So, so maybe an example would be like in medical use cases where you're making like a diagnostic test, and like it doesn't necessarily matter like how complicated it is or how long it takes to make the prediction. It's more like you want like the best model. They're everywhere on Kaggle, so kaggle.com. Like basically, if you want to win Kaggle, you have to use an ensemble. So you'll be forced basically to do that if you want to have any chance at winning Kaggle. So, you know, that's, I guess, an application, not necessarily like, you know, something that people have to do every day or have to do ever, but it's a fun thing to do. And yeah, so basically anytime you care about performance more than anything else is you should be using ensembles. And yeah.
My understanding is that when you combine different models, it's a linear combination, and it's not like a boosting where you are trying to give more weightage to the, like if you're using GLM, random forest, and deep learning, 3 models and creating an ensemble. So if the first one did bad on some data points, the second random forest is not trying to improve those, or is that also possible to use it as both linear combination and also like an iterative approach like in boosting?
So basically I think your question boils down to like what algorithm could you use for the meta learning step. So so a lot of times the linear model is actually really good, and the tree-based models don't work as well, although my colleague Brandon over there has told me that he's had a lot of success using GBMs as the meta learner. So I think you should always try using a lot of different types of meta learners. And if you use this package, there's a function that will just basically let you swap out different ones, and it's very easy to, you don't have to like retrain everything. You can just test each different meta learner and then pick the one that works the best. I mean, I've had success mostly using GLM or GLM with non-negative weights and deep learning. But so one thing that you just have to keep in mind is that in the meta learner, the input of the training data for the meta learner is very, very highly correlated data. So all of the columns are like trying to predict the same thing. So they're very tightly correlated data. So that's a little bit unusual for like your typical machine learning problem. So if you're, you know, trying to debug it, like keep that in mind that you're dealing with this like very highly correlated data that, you know, there's some algorithms that might not do a good job on that. So, but yeah, so the next thing that I should probably try is using Hyperopt or one of these other packages to find the best, the absolute best, not just, you know, random grid search, although there is a lot of, I think there's been a lot of papers that show that random grid search is quite good or better than you'd think it would be compared to some of these other methods. So random grid search is like kind of a quick and dirty way to get a very good model. And so another way would just be using one of these other techniques and then just maybe choose the top one out of each class. And then, yeah. So any more questions? Yeah.
So the input features to your meta learning step are the predictions from your base learners. And I've seen another technique where also the original input data is in that training set for the meta learners, so that the combination of the learners can sort of react to that input data. Have you done experiments to see, does that really buy you anything, and how much?
So yeah, so what Ray is asking is on this slide here where you basically, I go show you this slide where this the Z matrix here where you are training the meta learner, he's saying what happens if you just stick on like the original training data as well, because that's more data, has information in it. So I haven't actually tried that Yeah, I think I should, but I've read papers about it, and so so part of the reason I haven't tried it is because the all the theory behind it. Well, so this is I've only been out of academia for 1 year, so forgive me, but like all the theory says that this is the best way to do it, but sometimes that's not not the case in practice. So I have read papers where people have tried that, and they've tried all different versions of this, and I think there's been like mixed results. So I don't think you can rule it out. I think it's worth trying. It's just a matter of like adding that code to the package to do that, which I could do. So we should try that. Okay, anyone else?
Yeah, does anyone else have any questions? Okay, if not, do you have any announcements for the meetup group?
Let me think. I don't think so. I think our next meetup is going to be at Uber. I think it's going to be in September. But I haven't announced it yet. But so that's all I know. And then I was thinking that I wanted to do a meetup about predictive policing. So if anyone doesn't know what that term means, probably most people don't, but it's basically this whole thing that they're doing now where they're using like algorithms to predict like criminals and like all this stuff, and it's like super, like there's a lot of ethical issues that could be interesting to discuss. So if anyone has any ideas about that or wants to give a talk about that, I'm looking for some speakers to talk about that. Maybe that would be I don't know, after the Uber meetup. I'm not sure. So okay, thank you.
Cool. Thank you, Erin, and thank you all the speakers for talking here. Thank you all for attending. I have a tiny thing. We have well, not that tiny. We mentioned briefly the self-driving car nanodegree before. We have our director of learning for machine intelligence, Dhruv, here. And I'd just ask him to say a quick few words about how we're approaching the nanodegree and how you might be able to help us.
Yes, thank you. So what we're trying to do with the self-driving car nanodegree is take people with limited intermediate Python background and some machine learning background and take them into potentially coding a full self-driving car. And a lot of the techniques and ideas that you saw presented here are going to be applied throughout this program. So for instance, one of the first things we're going to do is try and get you to train a deep neural net to take you end to end from inputs, images, data, all the way to providing torque, to the steering wheel, acceleration data, and just going end to end completely. So it's a very exciting program. There's a lot of cool stuff, and we're looking for help in creating it and beta testing it and giving us feedback. So in particular, if you're interested in taking the program for free, giving us feedback and helping us improve it, let me know. We're looking for that help if you're willing to come in and do some user testing with us. We're also looking for people who are willing to potentially help teach some portions of it. So if you want to see your face on camera, help a lot of people learn about this field, we're looking for people to contract out and help us teach some of this. So come find me afterwards, and I'd love to work with all of you. Thank you.
Thanks, Dhruv. And yeah, if you have any questions for any of us, we're always around. Thank you all and have a good night.